Welcome to the Deep Dive. Today, we're unearthing a geological story, one with potentially huge implications for our future.
Yeah.
Imagine this giant volcanic scar on the Earth, the McDermott caldera.
Mm-hmm.
Now, picture it holding one of the world's biggest untapped reserves of lithium. The stuff powering our clean energy revolution. That's what we're diving into.
Absolutely. Lithium. It's critical, isn't it? For so many things we use every day. Your phone, electric cars,
Yeah.
all driving towards a hopefully cleaner future.
And it's superpower.
Well, it's basically packing a lot of energy into a really light element, ideal for rechargeable battery.
Right. And demand is just
Yeah.
going up.
Skyrocketing, yeah. As we switch to EVs and other tech.
Which brings us right back to McDermott. We could be talking 20 million tons,
Yeah.
maybe even up to 150 million tons of lithium.
It's a staggering potential amount.
The scale is just, it makes you ask, where did all this lithium actually come from?
Exactly. And it's not just lithium either. There's mercury, uranium, even gold deposits found there. It's a real geochemical puzzle box.
So our mission for this deep dive is to explore some really compelling new research that tries to answer that.
Right. We're focusing on a 2025 study. It's by Catherine E. Watts at the USGS, called Lithium from Magma to Mine in an Early Yellowstone Hotspot Caldera.
Magma to mine. I like that.
Yeah, and it gives us this unique window looking at the lithium content before the caldera even formed, locked inside ancient magma.
Okay, let's set the scene then. The caldera itself formed about 16.4 million years ago.
Roughly, yes. Right at the start of the Yellowstone Hotspot's journey across, the western U.S.
And it ties in with those huge Steens Flood basalt eruptions, too.
It does, yeah. Similar time frames, same sort of regional volcanic activity.
But what makes McDermott different from other Yellowstone hotspot calderas?
Ah, that's key. It seems McDermott, remarkably, stayed as a kind of closed hydrologic system for a very long time.
A closed system. You mean like water couldn't easily get out?
Precisely. Think of it like a bathtub with no drain. Other hotspot calderas often had complex faulting repeated eruptions, things that would disrupt that closed basin.
So any lithium dissolved in water just stayed there and got more concentrated.
That's the idea. It had nowhere else to go.
That bathtub image really helps. So those other calderas with the faults.
They acted like drains, basically. Any lithium-rich fluids could escape, so you don't get that massive accumulation.
Like Yellowstone today, with the lake and river.
Exactly. Yellowstone Lake, the river. It's an open system. There's lithium in the hot springs, sure, but it gets flushed out. No giant deposit forming.
Okay, so being closed is critical. What about that other caldera complex the study mentions? Nearby, northwest of McDermott. It had rich magmas too, apparently.
It did, yeah. Active around the same time, lie-rich magmas, but no major mineralization.
Why not?
Likely its structure, more complex geology, probably more faults, more fractures. It just couldn't maintain that stable, closed basin needed for the lithium to really build up, like at McDermott.
Got it. The long-term isolation was the secret sauce, maybe?
Seems like a big part of it, yeah.
Okay, let's dig into the evidence for these lithium-rich magmas. How on earth do scientists figure out lithium levels from 16 million years ago?
It's pretty amazing tech, actually. They use something called melt inclusions.
Melt inclusions?
Yeah, tiny, tiny little pockets of magma. They got trapped inside quartz crystals as the crystals were forming in this pre-caldera volcanic rock, a rhyolite.
Rhyolite, like a silica-rich lava.
Exactly. This specific one, Mendisuri, erupted just before the main caldera collapse, around 16.5 million years ago. And these inclusions are like perfect little time capsules.
Wow. Preserving the exact magma chemistry from that moment.
That's the idea. Unchanged, hopefully.
So what did these magma time capsules reveal? High lithium.
Oh, yeah. Significantly higher. We're talking 400 up to maybe 1,350 parts per million lithium inside those inclusions.
Compared to
the rhyolite rock around the inclusions, that only had about 20 to 70 ppm.
Whoa, that's a huge difference, like an order of magnitude or more.
It really is. It tells us the raw ingredients, the magma itself, was already unusually rich in lithium right from the start. It wasn't just the closed basin concentrating it later.
The source was already loaded.
Pretty much, yeah.
And this wasn't just a one-off thing at McDermott.
No, not at all. The researchers looked at data from 8 other calderas along the western part of the Yellowstone track. They found this recurring pattern. Lithium-rich rhyolitic magmas were actually pretty common there, often between 200 and, get this, 2,000 ppm lithium.
2,000 ppm, that's huge compared to normal crust.
Absolutely. That's easily 10 to 100 times the average lithium you'd find in continental crust.
But the study mentioned a difference, didn't it, between the western and eastern parts of the hotspot tract?
It did. That's another really interesting piece, the western part, where McDermott is.
Yeah.
Well, geologically, it sits east of these old terrains that sort of crashed into North America ages ago.
Okay.
And that area has a lot of what we call metasedimentary rocks. Old sediments, cooked and squeezed. And the theory is when those rocks melt deep down, especially water-bearing minerals in them like biotite, that melting process can naturally create magmas that are enriched in lithium. Biotite can hold a fair bit of lithium.
And the eastern part of the tract is different, underneath.
Yeah, mostly sits on much older, different kind of crust. The craton, dominated by rocks called granulate facies gneisses,
Which don't have much biotite.
generally no, or other hydrous minerals that easily release lithium when melted. So the magmas formed there tend to start out with lower lithium levels, below 200 ppm usually.
Huh. There's even some supporting evidence from another caldera, right? Caetano.
Yeah, good point. Down south, maybe 200 kilometers, they found these deep rock fragments, xenoliths, brought up there, biotite-rich metapelites, another metamorphosed sedimentary rock.
And their lithium levels.
Pretty high, 900 to 400 ppm. So it supports the idea that melting this kind of crust can give you lithium-rich melts.
So the type of crust the hotspot was melting through seems crucial for the initial lithium content.
It looks that way, yeah. A fundamental control.
But wait, the study also said the local rocks right under McDermott aren't super high in lithium themselves.
That's right. That's an important nuance. The older rocks directly beneath metasediments, granites, the Steens basalts, they generally top out around, say, 60 ppm lithium.
So even though the regional crust type favored lithium enrichment.
There must have been another process at work within the magma system itself to concentrate it even further before it got trapped in those melt inclusions or erupted.
Okay, which leads us nicely into the model for how the big deposit actually formed. What was that concentration mechanism?
Right. So the model starts with these andesitic magmas forming, probably from melting and mixing the Steens basalts and some of that basement crust.
Okay.
Then those magmas cool and undergo fractional crystallization.
Where minerals crystallize out, changing the leftover liquid.
Exactly. Plagioclase mostly, some pyroxene, feldspar, quartz, even a bit of that biotite we mentioned.
And as these minerals form, what happens to the lithium? Does it get concentrated in the remaining liquid?
Generally, yes. Like other incompatible elements that don't fit well into those crystal structures. But lithium's behavior was a bit variable, more complex than just simple concentration by crystallization, meaning other things might have been going on, maybe differences in how quickly things crystallize, or maybe some lithium escaped as gas, degassing from the melt inclusions.
Did the study look into lithium escaping, like leaking out of the inclusions
In
over
which
time?
they did consider that. Could it escape into gas bubbles or maybe get lost later if water got in, hydration? Well, the water content in the inclusions was moderate and didn't really correlate strongly with lithium levels, so probably not major loss through degassing or hydration.
Okay.
And the quartz crystals hosting the inclusions have very little lithium themselves, which argues against lithium just sort of migrating out as the magma around them solidified.
Right. So the high levels in the inclusion seem pretty robust. Okay, so we've got this extra rich magma. How does that lithium get from the magma into those lake sediments in the caldera?
This is where the whole system comes together. That closed basin is key again. It's likely a multi-stage process.
Stage one.
Stage one. As the magma cools and crystallizes deep down, it releases hot, chemically potent fluids. Magmatic hydrothermal fluids.
Carrying dissolved metals.
Exactly. Including lithium and, interestingly, uranium. Remember those inclusions where high lithium tracked with high uranium?
Yeah. Suggests they travel together.
Probably. And these fluids likely moved upwards along those big ring fractures formed when the caldera first collapsed.
Makes sense. Like plumbing.
And we see evidence for that uranium deposits are found right along the caldera edges, dated around 16.3 million years ago, just after the collapse.
Okay, so fluids escape along fractures. Then what?
Then comes resurgence. The caldera floor lifts back up that forms the Montana Mountains inside the caldera today.
Which means a big blob of magma pushed things up from below.
A large volume of magma emplaced shallowly, yes. And the model suggests this resurgent magma body then expelled more lithium-rich fluids.
A second pill.
Possibly multiple pulses.
Yeah.
And maybe fluids also leached some lithium from the already erupted volcanic rocks within the caldera itself.
And all this lithium-charged water ends up.
Trapped in the lake that formed inside that closed caldera basin.
So the lake becomes a big lithium soup.
Pretty much. And then evaporation kicks in.
Concentrating it even further.
Precisely. As water evaporates, the lithium concentration in the remaining lake water just goes up and up.
Until
Finally, it gets locked away, sequestered into the sediments building up on the lake floor. The study proposes it first got incorporated into a clay mineral called high-Eng smectite.
Which forms in evaporative conditions.
Awful does, yes. And then later, maybe during the heat associated with resurgence, that smectite altered to another clay, elite, which also holds on to the lithium.
So the clays basically grab the lithium out of the water and trapped it in the sediment layers.
That seems to be the most likely mechanism, yeah. It's quite an elegant step-by-step process when you lay it all out.
And the study actually tried to quantify this, like how much lithium could come just from the magma.
They did some calculations, yeah. Fascinating stuff. If you assume, say, 500 to 1,000 ppm lithium in the magma.
Which the melt inclusion supports.
Right. And a typical magma density, then even just 100 cubic kilometers of that magma, which isn't huge geologically, could contain 125 to 250 million tons of lithium.
Wow. The sheer amount is mind-boggling.
It really is. Puts the scale into perspective.
And that's just in the magma. What about the amount released into those fluids?
Using estimates for how lithium partitions between fluid and melt, how much prefers the fluid.
Yeah.
That same 100 cubic kilometers of magma could potentially release maybe 25 to 150 million tons of lithium into those fluids that escaped.
25 to 150 million tons. That range alone covers the entire estimated deposit size.
Exactly. And consider the actual resurgent magma body might have been much larger, maybe closer to 1,000 cubic kilometers, similar to the volume of the main eruption tuff.
So even if only a small fraction of that released its lithium,
it could easily account for the whole deposit, even the high end of the estimate.
Of course, there are uncertainties in these kinds of calculations.
Oh, absolutely. The study acknowledges that. Things like exact pressure, temperature, fluid salinity, how much water was actually in the fluid, these all affect how lithium behaves.
And it probably wasn't just one big whoosh of fluid release.
Likely not. Probably happened in pulses, maybe over a long time, as the magma crystallized, maybe got replenished. It's complex down there.
But the big picture takeaway seems clear.
I think so. The magma itself appears to have been a sufficient source for all that lithium. We don't necessarily need to rely only on leaching from the surrounding rocks, though that likely contributed too. It resolves that potential mass balance issue.
So bringing it all together, McDermott's magic recipe was this combination of, one, magmas that were already lithium-rich because of the deep crust they came from.
That initial enrichment.
And two, the long-term stability of that closed bathtub, that hydrologic system, allowing it to collect and concentrate over millions of years.
That combination seems to be the key. The right source material meeting the right geological conditions for preservation.
Which has big implications for finding other lithium deposits, right?
Definitely. It suggests that while lithium-rich magmas might actually be quite common in these kinds of volcanic systems,
the critical thing is preserving that closed basin.
It really seems to be. Lots of other potentially rich calderas might have just leaked, later faulting, tectonic shifts breaking the seal, letting lithium escape over time.
So McDermott was special because it stayed sealed.
For a very long time, yes.
It really does spark the imagination. Understanding these very specific, maybe unique geological histories, it makes you wonder what other places, maybe looking quite ordinary on the surface, might hold incredible resources if just the right sequence of events happened over geological time.
Yeah. What other critical metals, things we need for the future, are hiding out there waiting for us to figure out their particular origin story?
It's a pretty profound thought to end on. Thanks so much for walking us through this deep dive into McDermott's lithium secrets.
My pleasure. It's a fascinating story.